Hello, everyone. Welcome to my talk. In this talk, I will talk about the sub-Riemannian Ricci curvature where generalized gamma z calculus and functional inequalities. This is a joint work with Wu-Chen Li. Recent years, the Lagrange dynamics has been studied in the machine learning community, and a lot of algorithm has been designed based on this stochastic differential equation. So this is a particular gradient drift SDE with non-degenerate diffusion matrix. A lot of work has been done for this type of SDE. For example, the invariant measure and density, also the gradient flow for the density, and entropy dissipation, the convergence to the invariant measure. This Markov process is also associated with a semigroup. So people also study like the gradient estimates, Bakry and the log-Sobolev inequality for the heat kernel measure in this context. The entropy dissipation and the log-Sobolev inequality can be used to study asymptotic and non-asymptotic analysis in this case. So based on this analysis, people can do MC and Gibbs measure sampling. One of the important tools has been used in the literature will be the Bakry-Émery calculus, the so-called curvature dimension inequality in this case, which will give us the foundation to do algorithm designs. So one of the applications that I'm thinking of in our work would be this more general Lagrange dynamic, where we will consider this drift diffusion process where A will be a rectangular matrix, which is which is degenerate. So in this case, if you consider U, the temperature as a constant, so there has been some work to study the non-asymptotic analysis for this case. However, if U is a general function, there has not been work done in this direction. And in today's talk, I will try to provide our general framework and how we can apply in this case. At least we can get some partial result in terms of the asymptotic analysis. First, let me review some Bakry-Émery calculus. So first, let's see, for general operator L, we define the gamma of Fg will be in this form. In general, this will give us the first order operator. And the iteration of the gamma will be called gamma 2. You just change the product with the gamma for each of the term, then this will give us a second order operator. In general, for a second order operator L, the gamma 2 will give us the so-called Bochner's formula. For example, if L is the Laplacian operator on Riemannian manifold, we have the Heisenberg square plus Ricci curvature. And then this will imply the so-called curvature dimension inequality. So this curvature dimension inequality CD kappa n actually implies CD kappa infinity as n goes to infinity. So then by using the Bochner's formula, or say the curvature dimension inequality, this will help us to prove the log-Sobolev inequality. So in this case, the linear gross log-Sobolev inequality is in the following form, where on the left-hand side, this is the divergence, and right-hand side, left-hand side is the entropy, and the right-hand side will be the Fisher information in this case. And the CD kappa infinity will give us a proof for this log-Sobolev inequality. My question for this one would be, how about the degenerate operator, like the rectangular matrix for the Lagrange dynamics case, right? So let's look at the Heisenberg group, where we consider the horizontal Brownian motion on Heisenberg group is in this case. So now you see the diffusion matrix is rectangular, which is degenerate. So X and Y will be the horizontal direction. So we will have some horizontal Brownian motion in this case. This will be a video of the trajectory of the horizontal Brownian motion on Heisenberg group. You see the trend of the trajectory tell us some horizontal directions for this Brownian motion. Okay. In general, in this case, L is the horizontal Laplacian, and then the gamma 2 will be associated with this L. Unfortunately, this gamma 2 will give us the horizontal Hessian square plus this red term here. So this will by no way bounded below by the gamma. So the standard curvature dimension inequality does not work in this case. So in about 10 years ago, Bourdon and Garofalo, in this celebrated paper, they produced a generalized curvature dimension inequality. Instead of only having gamma 2, they also introduced the so-called gamma 2z, where you just replace gamma 1 with gamma 1z, where gamma 1z is the inner product of the vertical gradient. So in this case, they provide a generalized curvature dimension inequality. In particular, the Heisenberg group will satisfy this curvature dimension inequality with precise parameters. Most importantly, in this general framework, they need this assumption that gamma 1 and gamma 1z has to be commutative. Namely, the difference of these two trilinear form will give us 0. Okay, so if we consider the log-sub-law inequality for this sub-elliptic operator, where L satisfies the generalized curvature dimension inequality, so Bourdon and Bonnefont, with this assumption and also the inequality here, they are able to produce log-sub-law inequality for some measure and heat kernel measures. My question, I'll say, my main purpose for today's talk would be considered this case. How about we do not have the commutative property? So if this happens, what can we do? So this is our result. In this paper, we introduce a new gamma 2z operator, which was defined here. So we still have this gamma 2z, which we introduced by Bourdon and Garofalo. However, we have this new term introduced, the difference of the two divergences. Okay, if you remember the trilinear forms I mentioned before, in the work by Bourdon and Garofalo, they need this to be 0. So in this case, we do not require that term equals 0, but instead, we are able to find some equivalent representation. So the trilinear form can be transformed into this bilinear form, where this one can give us a new tensor, okay, a new tensor. So this is the new tensor, the rho star, where it comes from here, okay? So then the original Ricci curvature plus the new term will give us the new sub-Riemannian Ricci curvature, which will involve more examples which cannot be covered in the work by Bourdon and Garofalo for the generalized curvature dimension inequality. So this is a general Bochner's formula, and this will imply generalized curvature dimension inequality in our case. Okay. So here is another understanding for our work and the log-sub-law inequality. We know that on the left-hand side of the log-sub-law inequality, that's the divergence. So in here, we consider the KL divergence, which is the relative entropy reference to the rho star. The rho star here, we can think of as the density associated with the invariant measure d mu for the drift diffusion process, or say the sub-Riemannian horizontal Laplacian operator. So in this case, the Fisher information on the right-hand side will be different because here we have z. For the standard case, z is 0, then this is standard Fisher information. And then when we do the proof for the log-sub-law inequality, the first derivative of this Fisher information will give us gamma 2 plus gamma 2z rho star. You see here in the standard case, in the Riemannian case, this term is 0. In the work by Bourdon and Garofalo, if gamma 1 and gamma 1z are commutative, this is just the gamma 2z. Now, if we do not assume that term vanish, we have the new curvature or the new term gamma 2z rho star. Then, under this condition, by our curvature dimension inequality, we have the new z log-sub-law inequality. Okay, so this will be our main result in terms of introducing new sub-Riemannian Ricci curvature, which help us to do this one. Okay, so now I give you some example where you consider the displacement group. In this case, we can still define the horizontal Brownian motion x and y, the horizontal direction. In this case, this term is not 0. So the generalized curvature dimension inequality by Bourdon and Garofalo will not work here, so they cannot produce a log-sub-law inequality. And also, that framework cannot cover this step 3 condition. For example, the Indro group. So I will show you later that our framework will actually apply to these two examples. Let's consider a general drift diffusion process where A is the diffusion matrix, rectangular, and we have a horizontal gradient drift. And then the new sub-Riemann Ricci curvature we introduced can be transformed in terms of the matrix A, where the smallest eigenvalue of this matrix will imply the Z log Sobolev inequality. Okay, so now you see in this Heisenberg group, even in the Heisenberg group, let's consider a general horizontal drift in the dynamic, and we are able to have this matrix explicitly written. So if we consider that a particular potential V and consider a quotient on the Heisenberg group, then we will be able to find the minimum eigenvalue of this guy to be positive. For example, if you look at the video, so the green trajectory will be a horizontal Brownian motion. So it doesn't seem like have some concentration phenomenon. However, the blue trajectory will be adding the general horizontal gradient with this potential. We see some concentration in this picture. If you look at, if you compare this two picture, you see there is some concentration in the picture. So basically, in our framework for different groups, for example, the displacement group, we were able to compute the matrix A and find the explicit form. So once you pick a particular potential V, then we are able to find the condition so that the Z log Sobolev inequality will work for the weighted volume in this case. We are also able to find this one for the Angel group, which is a step 3 condition, which has not been covered in the literature. So all the results I talk about today are from these two papers. These two recent papers are on arXiv. Thanks for your attention.